The two-body problem, like we see with the planet orbiting its star, is one of the triumphs of physics. With Newton's laws, we can solve it exactly. The future of the system is written in its present. But add just one more body, and the problem changes completely. There's no exact solution. Instead, we can only approximate the future one step at a time, always at risk of a tiny error growing ever larger. This isn't a flaw in our methods. It's a fact of how complex systems behave. Some systems, even if governed by simple laws, don't easily reveal their future. In 1963, Edward Lorenz discovered that even a handful of simple equations could show the same unpredictable behavior. He wasn't studying space, he was modeling the weather. These three equations describe how a pocket of air moves when heated. The variable x measures the rolling motion of the air. Y tracks the temperature difference between rising and falling flows. Z tells us how heat builds up or escapes from the system. The constants sigma, rho, and beta set how quickly the air responds, how strong the temperature driving force is, and how fast the heat leaks away. On paper, this model might look simple, but in motion, it's anything but. Here are three systems with nearly identical starting points. At first, they follow the same path, but soon they drift apart, and they keep drifting. This sensitivity to initial conditions is the heart of chaos theory. And yet, no matter how wild the motion becomes, it never escapes a hidden boundary, the Lorenz attractor, a strange, folded shape set by the very rules that define the system. The Lorenz attractor shows us that even when the rules are simple and the system is deterministic, the future can remain out of reach, simply because chaos is part of nature.